Alright, let's begin. So, I wanted to start by just like addressing an issue I've seen come up in the past. So, this is like going to be a calculator exercise real quick. So, hello. Calculator, if you have a graphing calculator, then get to graphing mode, otherwise I'm going to ask you to like compute some things. You probably see a button on your calculator that says like sine inverse or something like that. And you might think, oh, obviously that should be like doing reciprocal in sine. That's what raising to the -1 means. Well, if you've got yourself a graphing calculator, graph both those things. So literally 1 over sine of x, or sine inverse of x. If you're someone who's got like a standard scientific calculator instead, oh gosh, let's pick a number. 7.
It looks like it's working.
And let's see. So those of you who are using like graphing calculator, tell me about the graphs you line up. They look the same? Nope. Those aren't the same function. The calculator means something different by sine inverse. Those of you who just like evaluated these two things using the like standard scientific calculator, tell me about sine inverse of 7. What'd you get? 1 over sine inverse of 7.
Over sine inverse or 1 over sine?
Oh, sorry, 1 over sine of 7.
0.12.
Are you sure? Not 1.2?
Yes. Oh, and you agree.
Yeah, it shouldn't make a difference. Well, it will make a difference in what your number is. That should be bigger than 1. Alright, so 1 over.
Never mind.
Cool. So I guess this is in degree mode, it looks like. No, it's in radian mode. No, it's in degree mode. About 8.2. If you're on radians, 1.5-ish.
Yeah, that's just
What about inverse sine of 7? So that's kind of neat. Here's the takeaway, sine inverse. The like inverse trig buttons on your calculator don't mean those central trig functions. So, what do they mean then? That's what we'll start in on today. These are the so-called inverse trig functions. And the way I want to lead into this is like, let's start with a reasonably explicit example. So let's suppose I give you a right triangle. By measuring, we find that the opposite side from some angle is 1, and the hypotenuse has an angle. Well, given this right triangle, what's the sine of theta? Not what's theta, just what's the sine of theta?
Where are you going?
1 over, right? So total. Sine is opposite of the hypotenuse. Let's also get some bounds. What's the biggest angle you could possibly see for that? Like what range of angles might you see for theta, given that this is a right triangle? Probably can't see anything negative. And probably 0, you shouldn't be able to get that angle. But I could squeeze it really small down. What's the biggest that angle would be?
not 90, but it was supposed to be.
Just shy of 90 degrees. 90 degrees slash pi over 2 radians. So it's often useful to now be able to like say what angle is that. That's the job of inverse straight functions. The angle you see in this triangle with opposite side 1, hypotenuse length 8, is called sine inverse of 1 over 8, or sometimes arc sine of 1 over 8. Or sometimes, depending on the calculator, it's abbreviated all the way to a sine 1 over 8. So take a moment and look at your graphing calculator. On your, well, whatever calculator you use. Do you see a button just labeled sine inverse? And you don't have a button that says like a sine instead? Ah, okay, cool. Right, so there's no point in labeling that way. Now arc sine is useful to know what that means. Use that, get me an approximation. Use your calculator. Tell me what inverse sine of 1 over 8 is.
Yeah.
I hear a 0.125. Do I hear a different value from anyone? What do you got?
I got 7.18.
7.1. Any guesses as to why they're different?
Degrees versus radians.
Could be degrees, lots of radians. What modes are you in?
I'm in degrees.
Degrees.
Radians.
Radians. And I guess that makes sense. Yeah, 7 degrees is like a pretty small angle. I bet if you take this and multiply it by pi over 180, you'll get something about that. Neato. Cool, I feel pretty good. So there's the inverse trig functions. These are just the functions that say, what value do you want the trig function to have? I'm going to give you the angle that gives you that output value. That's what these inverse trig functions are. And maybe here's the best informal definition to give. Inverse sine of t, I give you the number t, you compute inverse sine, is the simplest, in air quotes, angle whose sine is t. Cosine, inverse, should then be, I don't know, the same thing. The simplest angle with cosine theta equal to t. Similarly, inverse tangent is the simplest angle whose tangent is equal to t. Alright, well, that's all well and good. So these are like inverse functions to the trig functions. That's why there's the superscript -1, because these are inverse functions to the trig functions. Well, let's notice something goofy here. There's the graph of sine and cosine, or cosine and sine. Let's remember which. Of those two, which one is sine? Left or right? That one's sine? Here's the graph of y equals sine x. There's the graph of y equals cosine x. You take a look at either of those two. Those functions 1 to 1. Do they pass the horizontal line test? Yeah, they do. I draw a horizontal line. Yeah, the vertical line test is just, is this thing a function? The horizontal line test is what you do to ask if this thing is a 1 to 1 function. How many times does that green horizontal line cross y equals sine of x? About 4 times if you count this picture, but the picture keeps going in that direction. It's like infinity times. These functions are very badly not 1 to 1. They're like infinity to 1 functions. So that's kind of off-putting because, like, if I take this graph and I like swap through all of x and y, is that going to pass the vertical line test? No, so this thing doesn't have an inverse function. But we've like overcome an issue like that in the past. Here's another example of a non-one-to-one function. Here's y equals x squared. Is that thing 1 to 1? But if I just need to undo the squaring function, what function are you going to tell me? The square root function. So how is the square root function defined? Well, for any possible output values, there's like a positive and a negative choice that gives you that value for the square. The square root function is given by saying, well, screw it, I'm only going to record the positive one. So throw out half of the domain. If I just see that pink graph as a 1-to-1, that has an inverse function. That's how you get square root. Let's do the same thing over here. I want the simplest possible angle, so I'm going to like start at 0, because 0 is like the simplest angle I can think of. How far to the right on sine of x can I go and still have sine of x be 1-to-1? I hear a pi? Do I hear a second go pi? Do I hear a disagreement with pi? I disagree with pi.
Okay, like just up to it, so that it doesn't like match 0. Is that what you're saying?
No, pi's too far. Because pi's like there.
Half pi or
Half of pi. Right? The max of sine happens at pi over 2. That points at x equal to pi over 2. You can go up that far before it stops being 1-to-1. How far back can you go and still have it be 1-to-1? Well, sine's off, so there's probably some symmetry, right? We can make it to like there, and what x value should that be? So that pink highlighted bit of the graph of sine of x is 1-to-1. So if I forget the rest of the graph of sine of x, is that function I can find an inverse function to. Let's do the same thing for cosine. Let's start at 0, and we'll start going right. How far to the right can I go and still have cosine be 1-to-1?
Well, especially when it's criteria for
Let's think of it this way, like, without like computing the number, like it's up to there, right? Beyond that, it's going to automatically stop being 1-to-1. So that's like the first time when cosine is -1. What's the first value where cosine is equal to -1? Pi. So here I have x equals pi, starting at x equals 0. If I only see that much of the graph of cosine, is it 1-to-1? Nice. The inverse of that function is what I'm going to call inverse cosine. Groovy. Well, there's like the very sketchiest, of definitions. Let's use those. So, right here I have redrawn those exact same bits highlighted. On the page. You look at those, they want 1. Nice. So this is called a restricting domain. I'm going to take the exact same function, I'm just going to trim the domain down so I don't see whatever bad behavior I don't want to see. I don't want to see non-1-to-1-ness. I can use that much of the domain without having it be not 1-to-1-ness. So, let's read it up now. If I just give you the graph that is that picture, given by that picture, what's the domain of that function?
negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. Should I include or exclude those endpoints?
Include.
Include. Solid dots, right? And I want to go as far as possible while still having it be 1-to-1. I can include the solid dot and still have it be 1-to-1. What's its range? -1 to 1, including endpoints. So that's good. That means that I still hit all of the possible output values for sine. It would be annoying if I missed some. There's the graph of cosine after I restricted domain. Answer the same question. What's the domain now?
0 to pi.
0 to pi. And its range?
-1 to 1.
-1 to 1. And I think I'm going to come back up to this, the definition bit. So I told you what like the inverse trig function should be. I'm going to invert those functions. So that means I guess I need to swap the x and y values. So the point negative pi over 2, negative 1 is going to become negative 1, negative pi over 2. Pi over 2 comma 1 is going to become 1 comma pi over 2. And then I just need to get between them by like swapping the role of x and y. So I guess another point I see on the graph, this graph, is 0, 0. So what graph's going to be on the inbox function? What point's going to be on the graph of the inbox function? Still 0, 0, right? When you swap the 0, we go into 0, it's still 0, 0. And let's see, here I see like, that's about like slope 1-ish, still going to be slope 1. That's the point where the minimum happens, it like flattens out there, so I should see like basically a vertical line here or there. And it's going to go in between. So there's the graph of sine inverse of x. Those of you who went and like graphed inverse, sine inverse of x using the graphing calculator, does that agree with the graph you saw? Cool, yeah. If it didn't, then you were probably in degree mode. Because notice, like, it makes a difference. And we'll, like, explore how it makes a difference in a minute. Let's do the same thing for cosine. 0, 1 is on the graph of cosine. So 1, 0 should be on the graph of inverse cosine. Pi negative 1 is on the graph of cosine. So negative 1 pi should be on the graph of inverse cosine. Pi over 2, 0, 0, pi over 2. And then populate between. There's the graph of inverse cosine. Cool. That feel pretty good? And now let's like write down the formal definition. So remember, like, inverse trig functions are supposed to be things like swap, domain, and range. So let's use that. Well, we computed the domain of the thing after we restricted domain and the range. So let's compute the domain and range of inverse sine using that. What should the domain of inverse sine be? What happens to domain and range when you take an inverse function? They switch. Right, because domain has to do with input values, range with output, and inverse functions like swap input values with output values. So, what's the domain of inverse sine? Negative 1 to 1. What's its range?
Negative pi over 2 to pi over 2.
Oh, cool. Does that agree with this? The picture we drew? Nice. And let's do the same thing with inverse cosine. What should the domain of inverse cosine be?
Negative 1 to 1.
Negative 1 to 1. And what should its range be?
0 to pi.
0 to pi. And maybe now we see why inverse sine of 7 gave you a domain error. I can't plug 7 into inverse sine. 7 isn't in the domain. And notice it kind of like it can't be. This would be like asking what angle gives me a sine value of 7. But the biggest sine is just 1. Neato. Alright, so here's like the most formal definition now. So inverse sine of t, also known as arc sine of t, is the angle that lives in the range of inverse sine in between negative pi over 2 and pi over 2, which satisfies sine equal to whatever that input value is. Similarly, cosine inverse of t, also known as arc cosine of t, is the angle whose cosine is t, and which lives in the range of inverse cosine. So what does this angle have to live between? Cool. Alright. So, those are the inverse trig functions. Well, there's inverse sine and inverse cosine. Do you think we could do some similar stuff here, like inverse tangent? And we will, like next time, I think. Could we do something similar to get like inverse cotangent or inverse secant? Yeah, we could. We won't. I'll kind of ignore those. Nice. Alright. So, here's the next thing I want to point out. You know how to compute these at least at some points. So let's read something off. So let's try to compute inverse sine of 1 over 2. And let's think about what I need. I need to compute that. I need an angle with sine equal to 1 over 2. And I need this to be in between negative pi over 2 and pi over 2. Alright, how many people still carry that units orbital with them? You should, right? Take it out. and use it to answer that question. Alright. So looking at that unit model, what angle do you see whose sine is 1 half? I hear pi over 6. And just for the sake of completeness, is there another angle you see on the unit circle where sine is 1 half? What's that other angle? 5 pi over 6. No, my unit circle is filled out incorrectly. No, that's fine. Okay, yeah, that's the tangent. Cool. I can't read it. Okay, so here are two candidates. It can't be both, right? It's a function. Now let's ask about these two things. Which of these two is in between negative pi over 2 and pi over 2? Pi over 6 is? Pi over 6, is it? Cool. So you can use your unit circle to compute inverse stroke functions, at least at a few particular input values. Cool. That feels pretty good. Nice. Again. Suppose I ask you to compute, not sine inverse, but cosine inverse of negative root 3 over 2. What are you going to tell me? I hear a pi over 6. Do I hear a second for pi over 6? Cool. Yeah. Right, I want cosine to be negative 3 over 2. Cosine's negative 3 over 2. And 5 pi over 6, also a negative 5 pi over 6. But what range does inverse cosine have to live between? 0 to pi. So 0 to pi. Yeah, there we go, 5 pi over 6. Neato. Groovy. That feel pretty alright? Nice. Let's go back to the example we started with. So here's like a right triangle. It's a right triangle where I know that the adjacent side is length 2, the hypotenuse has length 5. Is that enough information to determine everything about that triangle? And I guess what do I mean by everything? I mean, I want to know alpha, I want to know beta, I want to know the side length, and I don't care what order you tell them to be in. So let's just try to figure out all of those. Oh, cool. Looks like people are just like going for it. People see how to make progress on each of those just automatically. People want me to say anything? Cool. So you know hands go up from me how I say some things. I will wait for people to tell me what things they get. Need to like talk to each other. Compare.
specify, but make sure you're answering code. Whether you are reporting things being radians or degrees. I don't think it'll matter for the side length A. But for alpha and beta, you'll either be in radians or in degrees. And as long as you communicate which, I'll be happy. If you don't have a calculator, then honestly you're probably happy with like exact numbers instead of decimal approximations. Because I'm gonna ask you. Yeah, because the cosine of alpha is 2 Yeah, I'm going to nitpick the way you write them out. You mean alpha equals inverse cosine of 2 bits. Neato. Let's come together and talk through this. So, I guess there's the one of the things here that like you don't need to do any inverse trigonometry to find, right? The side length A you could just compute. What is the side length A? I hear square root of 21. Cool. You guys see enough heads nodding, I'm happy. I didn't do it. And if you wanted to get like a decimal approximation, you could, but I don't think I want to. All right. What about alpha or beta? I guess alpha is the one I've written on top. What is? How do you compute alpha? I hear cosine inverse of 2 over 5. Do I hear a second for that? Cool. Let's see, could we also theoretically have used sine inverse of root 21 over 5? Yeah, and in fact, let's do that to do a sanity check. Compute for me inverse cosine of 2/5. Well, you already have done that. Compute for me also inverse sine of root 21 over 5. They give it the same answer? Nice. What answer is that? Give me the decimal value. Cool. And based on the size of that number, do you think you're a degree or radian? Well, that's kind of a big number for your radians. In particular, it's bigger than like pi over 2, which is the biggest thing you can see in a triangle. What if you were in radian mode? Anyone do that in radian mode? What'd you get?
Yeah, 1.15.
So I guess I'll add that up to 6. That's enough to do this one. Cool. How about beta? What was beta? And I guess same thing. I want the exact value and then like a decimal approximation. Sine inverse of 2 over 5. I guess I could have done this also, but let's not. What is that about? 0.41 radians, and when I don't specify a thing, angles are in radians. Anyone do it in degrees? Okay, so 23.3.
Okay, 9:30 here.
I'm going to round that up to 3. Cool. So what's the point of this example? Inverse trig functions let you solve the right triangle. If I give you something that's just built out of a bunch of right triangles and you need to find some angles, you're going to need to do some inverse trigonometry. And there's no like weird subtlety in like the fact that we restricted domain in this. Because what angles can you see in our triangle? Angles between like 0 and pi over 2. Well, angles between 0 and pi over 2 are also in both of those output ranges. So we'll get acceptable answers using inverse trig functions. what I'd like to do with the rest is some like weird stuff that can happen with inverse trig functions. And let's start with like something that's relatively normal and not surprising. Let's compute from the inside out. Let's compute cosine of inverse cosine of 1/2. I guess first things first. Let's look at your unit circle. What is the inverse cosine of 1/2? Taking a glance, I want inverse cosine of 1/2. So what's the angle in between 0 and pi? That's inverse cosine is what I want. Whose cosine is 1/2. Cool. All 60 degrees if you're in degrees. All right. But what is the cosine of pi over 30 then? You're 1/2, right? Because like what happened there, I said, oh, I'm going to give you the x value of 1/2. What angle is that? That's pi over 30. Oh, what x value comes from pi over 30? Well, it's 1/2 because like I just told you that in the opposite direction. So let's do that one more time. Sine of the inverse sine of -1. So step 1, compute the inverse sine of -1 using your unit circle. What's the angle you see whose sine is -1?
Pi over 4.
Nope.
Pi over-
So let's remember. So it's going to be like, there's the sine that's -1. And I need to represent this as an angle in between negative pi over 2 and pi over 2. So I can't use 3 pi over 2 because that's not in between negative pi over 2 and pi over 2. What angle should I use?
Negative pi.
But that subtlety, I think, doesn't affect the end result because you got that negative pi over 2 by asking when is y equal to -1. So what's the sine of negative pi over 2?
-1.
Because that's how you got that damn angle. So maybe you think to yourself, oh, that should mean that like trig function of same trig function inverse of input should always be that same input. But let's see that failing. Suppose I ask you to compute cosine of the inverse cosine of 12. And let's start with inverse cosine of 12. What is the inverse cosine of 12? What angle corresponds to a cosine equal to 12? What's the biggest cosine can be? Is there an angle whose cosine is 12? No, it's not that like, it's not on the unit circle. It's that it would correspond to an x value like way over there. That's not on the unit circle at all. Oh, well, so, yeah, it isn't. There is no cosine of inverse cosine of 12. It's not 12, it just isn't anything. But as long as that doesn't happen, yeah, cosine of cosine inverse of x is always x. Sine of sine inverse of x is always x. At least as long as that x value is a legal input for an inverse trig function. It has to be between -1 and 1. Nice. So nothing so weird, yeah, just like you restricted domain, so of course you can have some domain going on. Something weird happens when you do inverse sine of the sine of theta or inverse cosine of the cosine of theta. In that, well, you're going to wind up getting like these weird sawtooth graphs. And so maybe I'll tell you this. One of these is inverse cosine of cosine of x equals y. One of these is inverse sine of the sine of x equals y. Let's try to decide which one. And let's do it by like plotting some points. I think x equals pi will do because at x equals pi the two graphs are different. So let's do it. Let's compute inverse cosine of the cosine of pi. What's the cosine of pi? -1. Because you look at your unit circle, you go over to an angle of pi, you record the x value. All right, now let's compute the inverse cosine of -1. So, the range of inverse cosine is 0 up to pi. So what angle in between 0 and pi gives you cosine equal to -1? Oh, cool. So, inverse cosine of the cosine of pi is pi. That's a really bad from pi. It's a little pi. So I guess that means that x equals pi, y equals pi, pi is on y equals cosine inverse of the cosine of pi. So, between these two options, which one might be cosine inverse of the cosine of x? Oh, there should be an x there. Cool, so I guess that means that if this is the graph of inverse sine of the sine of x, then what output value had better correspond to an input value of pi?
Zero.
Better be an output value of 0. Pi had better wind up being 0. And let's see if that actually happens by doing the same computation. Take a look at your unit circle. What's the sine of pi?
Zero.
Alright. And now, inverse sine of 0, that's like the simplest angle whose sine is 0. What's the simplest angle whose sine is 0?
Zero.
Oh, cool, check that. That also tells you maybe that, like, computing something that looks like inverse trig function of an input might be, like, a little bit complicated. Especially as, like, the input gets big, maybe it's hard to tell whether you're on one of the upward sawtooth or downward sawtooths. Or, like, which one that one should live on. So, with the remaining time, yeah, it's plenty of time, about 2 minutes. I'd like to talk about exactly that problem. Let's try messing around with trying to compute things that look like sine inverse of the sine of an input, or cosine inverse of the cosine of an input. Oh, and maybe I'll have you do this to check too. Let's do this for another like experiment in like, does radian versus degree mode matter? Do you think this will change if I go radians versus degrees? Folks go yes? Folks go shouldn't make a difference? Cool. And that's like intuitive, right? Like you're undoing the trig function anyway, so like, what difference should it make? Those of you who say yes, what sort of difference do you think it should make?
I just thought that maybe it does for the normal ones and it might for these two.
Okay, that's fair enough. Let's do it. So, well, I don't know if it does my graphing calculator now. Alright, so let's do it for sine or do it for cosine. Do it for sine? Do it for cosine. Cool. A few hands go up for cosine, it doesn't really make a difference, though, does it? Arc cosine of x. By looking at that, do you think I'm in radian mode or degree mode? I suspect radians, because that's about pi pi. Let's change to degree mode. Oh, interesting. Right now that just lets the graph in absolute value. Let's adjust that viewing window. Or like, let's just like zoom out. Oh hey, see that same sort of sawtooth happening? What do you think that turnaround point is? It's like, this where it changes from up to down. What angle do you think that might be?
180.
Looks like it's about 180. Oh hey! What's pi radians in degrees?
180.
Cool. Yeah, and I guess that makes sense. Cosine takes an input that's an angle. So whether you measure the degrees in radians or degrees matters. That translates it to like a point on the unit circle, and that translates it back to an angle, which, oh, I guess now it's in degrees. Groovy. So, Now let's do some stuff with this. Oh, maybe, no, I'm gonna flip back again. This result is independent of degrees, bosses, radians. Because this says I start with the thing that I'm plugging into inverse cosine, so that's like a point on the units angle. Inverse cosine translates it to an angle in degrees or radians. And then cosine translates that back to like the x value on the units angle. So this one won't matter whether you're on degrees or radians. All right, so how to compute. So here's the idea of what these questions are always asking. If I ask you to compute the inverse sine of the sine of alpha, what I'm asking you to do is to give you the simplest possible angle whose sine is the same as the sine of the angle I give you. That seems sensible? Like a reasonable question to ask? That's exactly what this is. And let's try to do it in practice. Oh, let's remember what simplest means. What's the range of inverse sine? No, domain of inverse sine. No, I want the range, because this is an output value. This should say range. What's the range of inverse sine? Negative pi over 2 to pi over 2. You'll notice maybe that I've been saying like this question, what's the range of the inverse straight function, an awful lot today. I suppose that's maybe because I think that idea is like important. What about the range of inverse cosine?
0 to pi.
0 to pi. So that's what I mean by simple. So I ask you for the inverse sine of the sine of 27 pi over 5. I'm asking you, what is the angle in between negative pi over 2 and pi over 2, whose sine is the same as the sine of 27 pi over 5? That's what I'm going to try to do. And here's the way, like an algorithm that I'll try to follow. 27 pi over 5, that like is an angle that's way bigger than 2 pi, right? So it's got some extra 2 pi's floating around. Let's try to find them. And let's do that by writing 27 pi over 5 as like a whole number times pi plus what we know. Oh, we've done that a few times, right? So do it. Realize 27 pi over 5 in this nice form. How many full pi's are there? 5. And how many are left over? Well, 2/5. Alright. How do you compute that? Like what's the like short answer for how you find those things? You do like long division, right? And you want me to actually do it? Okay, cool, then I'll do it. So you want to do 27 pi over 5, so let's do that. 27, I'll divide 5 into it. Just doing the normal like long division stuff. How many times does 5 go into, 5 doesn't go into 2. So you go to the next digit, how many times does 5 go into 27? 5 times, because that's like 25. Put a 5 there, 5 times 5 is 25, you subtract the result, that gives me a 2. How many times does 5 go into 2? It doesn't. So you just have a remainder home. So this 5 is that 5. This 2 is that 2. And then you just put the pi back. Alright, so let's draw a picture of that and throw out any excess 2 pi's. So I'm going to draw myself a unit circle. So I'm going to start by counting out 5 pi rotation. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. And now I need to do an extra 2 pi over 5. Let's see, 2 pi over 5 is less than half a pi. So I think it should be there. What quadrant does that live in?
3.
Quadrant 3. Let's just hold on to that one. Alright, so first things first. Let's throw out, like there's some extra 2 pi's, right? And that there's a 4 pi I could get rid of. So I could rewrite this as instead just pi plus 2 pi over 5. Because that would just be like going forward by pi and then divided. Alright. What's the range of inverse sine?
Negative pi,
Negative pi comma pi.
pi, pi over.
Yeah, over 2. Negative pi over 2 pi over 2.
Yeah.
What quadrants does that give you on the unit circle?
1 and 4.
1 and 4, because there's negative pi over 2. Oh, so this angle, is it even in the right quadrant? So I need to accord the same sine value, so the same y value. But I need it to be in quadrant 1 or 4, so I guess I need to like reflect it over the y-axis. Doing what to an angle results in flipping over the y-axis? Do you remember? And let's maybe see like all of them. What do you do to reflect over the x-axis? Instead of rotating up, want to rotate down. Like what's the difference between those two angles? They're negatives of each other?
Yeah.
Okay, cool. So that's how you reflect over the x-axis. I want to reflect over the y-axis. So I guess here's, wait, which way is the positive direction? This way is positive, right? Okay. It's how we're going to face in our direction. So I want to like go up and then this one should be going like the opposite direction. Oh, cool. So it looks like this one's going negative. It's going to be like a negative sign. But I start by going over by pi. So pi minus theta. Cool, let's do that. So when you reflect over the y-axis, you do pi minus theta. So let's do pi minus this angle. Oh, cool. Simplify that. What's pi minus 2 pi? What's pi minus pi plus 2 pi over 5? Let's just minus 2 pi over 5, right? Like that. This and that will cancel. Negative 2 pi over 5. Alright, so there's like the simpler angle I have, so that's like this angle. Negative 2 pi over 5. And all of those angles have the same output value as the sum, as the thing I started with. So now let's just see if this is good enough. Does this have the same, well, it definitely has the same sine value. Is this thing in between negative pi over 2 and pi over 2? Yeah, cool. So what up? And there's a lot of moving parts there. So I'm going to encourage one like double check. Because I'm probably going to ask you problems like this on the homework. There's no reason to like have these answers wrong because you have calculating machines. Take out your calculator. Make sure you're in Radian mode. And compute for me arc sine of the sine of 27 pi over 5. Tell me what you get. Depending on your calculator, maybe it'll give you a decimal value. That's kind of what I want the most right now. So I hear a negative 1.26. Do I hear a second for that? Nice. If I want to check if this is reasonable, let's also get a decimal approximation for the thing I think the answer is. Tell me, what is negative 2 pi over 5? I like the negative sign. Is it the same? Nice. So, on things like the open-ended homework one day, where I'm going to ask you to go through a small process for this. Going through this process, start with the angle you want to study. Do this division step. Throw out any excess 2 pi's. Maybe you're left with an extra pi. Draw that angle on the slide. See where it is. Is it in a quadrant that's okay?
If so, great. Otherwise, you need to do a reflection. After you do the reflection, ask yourself again, is it now an acceptable angle to be in output for that inbox income? If it is, great, there's your final light off. If not, then maybe you need to add some extra keypoints. And in fact, maybe here's a good idea. You'll notice I didn't do the think volume loss cosine yet, because I'm out of time. I kind of want to start with that, but like, it'd be better if you do it false. So, I'll find some time in the next 23 hours to do that excellent example.
Probably not.
So, what's the domain of this is entirely computerized. And the why Here is, I have a meeting immediately, so I can't spend so much on this. But here's what I'll have you do in the meantime.
Different like locations for work.
So all of those have family tools. And
So I'm just like.
more than correctly, yeah? Okay, so it can be done.
Yeah.
Yeah, right, like, this seems like, it could be a matter of like, doing the manual type.
Yeah.
Seeing like how to do it, so that might be like, really opaque, start to.
Yeah, I was thinking
Yeah,
I'll
like,
figure it.
start with a Google search and like,
Yeah.
when you to like, probably a Stack Exchange. Yeah.
Have a good day.
You too.